Hello dear students. In our today's article we are going to study about the topic of Lensmaker's equation. So what is Lensmaker's equation? It is nothing but the relation between refractive index, focal length and radius of curvature r for any type of thin film. So this relation is called as Lensmaker's equation. So we are going to derive this equation today. To derive this equation, we must have one ray diagram. Okay, in this diagram, if we see one biconvex lens is there, this lens is constructed by using two curved surfaces. Okay, two curved surfaces which are made up by using two spheres, imaginary spheres having their radius of curvatures r1 and r2. The object is placed at point O on principal axis. When this object faces the front side of the lens, which is front surface, the ray emitted from point O will travel along the principal axis is undeviated. Okay, the ray which is traveling through pole at point P will travel undeviated, but the paraxial ray which is traveling towards point A at the front surface of the lens, the ray OA, which will deviate towards the normal. Okay, the normal drawn on the front surface of the lens, and it will eventually intersect the principal axis at I1. Okay, we can see that line is given by dotted line, and this is the virtual image formed because of first surface of refractive index n. Okay, the medium of lens is having refractive index n with respect to surrounding. So the outside medium of lens is obviously air. That's why its refractive index must be 1. Okay, as we know, refractive index of air and vacuum is 1. Then for the second refracting surface, we can see intermediate ray will travel towards the point B, and then it will form the image at I1. Okay, the virtual image will be seen at I1. Here the image will be seen virtual. That's why we can get the equation that we have already derived in last lecture. Okay, the relation for refraction by spherical surface. We have already derived that equation, which is given on your screen, which is n2 minus n1 upon r, which is equal to n2 upon v minus n1 upon u. So this equation is we have already derived, and this equation is true for virtual image formed at I1 for object O. Now if you put the values for this virtual image in that particular equation for the first surface only, as refractive index of the lens medium is n2, which is considered as n, then air medium has refractive index is equal to 1. That's why n1 is equal to 1, r is equal to r1, because we are talking here about first refracting surface. Image is formed at I1, which is distance v1 from pole. That's why image distance v is equal to v1, and object is kept at distance u from pole. That's why object distance is u. So if we put these values in above equation, then we will get equation number 9.5. n minus 1 upon r1 is equal to n upon v1 minus 1 upon u. So this is our equation number 9.5, which is holds true for first refracting surface when ray OA bends towards principal axis, give you virtual image at I1. And then the equation for this refraction is given by equation number 9.5. Now our next equation is equation for refraction after second surface of refractive index R2. Okay, if we consider this diagram, the second refracting surface where point B is located, the ray will bends towards principal axis and will reach point I. Here we will get real image. Okay, and for this real image I1, the virtual image, will act as an object. Okay, for real image I, virtual image I1 will act as object. That's why here we should consider the value of V1 as U, because object distance U must be equal to V1, and this is the reason behind that I1 is the virtual image and it will act as object for real image I. Okay, this is the important thing we have to understand. If we put that value in equation 9.6, okay, we can see in this equation 9.6, here N2 is air medium, that's why it will be taken as 1 as an refractive index, and N1 is the material medium having refractive index N, so 1 minus N upon R2, because we are talking about second refracting surface having radius of curvature R2. That's why we have to consider here 9.6. By rearranging some terms in this equation, we can take N minus 1 upon minus R2, and on the RHS, the distance of image, the real image, is V from pole. That's why 1 upon V minus N upon V1. The value of V1 is the object distance. Now we can add equation number 5 with equation number 9.6. So after addition we will get these two equations, 9.5 and 9.6 will give you N minus 1 into 1 minus R1 minus 1 upon R2, which is equal to 1 upon V minus 1 upon U. Because here if we see in equation number 9.5 N upon V1, and in equation 9.6 minus N upon V1 is there, so both these values will get cancelled with each other, and then we will get 1 upon V minus 1 upon U on addition. So this is our equation. Now for this equation, if we consider U is equal to infinity, that means the object is kept at infinity according to the rules of optics. When your object is kept at infinity, your image distance will be f, the focal length. Okay, the image will appear at focal length of that lens. Now rearranging the above equation, we will get 1 upon f is equal to n minus 1 into 1 upon r1 minus 1 upon r2, because in our above equation u is infinity, that's why 1 upon infinity is 0, and v is equal to f, that's why 1 upon v is equal to 1 upon f, and that value is kept on LHS, and RHS is as it is. So this is our equation number 9.7, and this equation is called as lens maker's equation. So this is how we have derived our lens maker equation that we have studied in our today's lecture. So that's all for today. Thank you.